Okay, so last lecture what we saw was that the action for a field can be written as an integral over time as well as space over some Lagrangian density, which is a function of the field and its derivatives. Again, remember the derivatives include both spatial and time derivatives, and we also saw that the structure of L should be such that the spatial and time derivatives combine to give you this Lorentz scalar, and all that remained, if you restricted yourself to two derivative pieces out here, is a part which corresponds to the ultra local interaction. So, in continuum field theories, one loosely refers to this term as the kinetic energy term, even though it has the local part of the spatial part, derivative part of this is actually not truly a kinetic energy in the sense of classical mechanics, but but nevertheless this is the general structure. We call this the kinetic energy, and this we will call the potential energy. So, the thing to do next is to use the action principle to determine the Euler-Lagrange equations of motion. Equation of UM is short for equation of motion. So, this is what we need to do. So, it is fairly straightforward, but what we will do is make a slight detour into what I call functional calculus, but it is probably better to call it calculus of variations, because apparently there is something else in mathematics which is also called functional calculus, which is not quite the same as this calculus of variations. Okay. So, let us go back to just normal classical mechanics of a single degree of freedom or finite number of, let us choose finite degrees of freedom. So, in such cases the action principle was quite straightforward. So, as usual I will use the 1 degree of freedom to draw pictures, but later we will generalize. Okay. So, the problem is as follows. This is something which we discussed long ago in the maybe in the first lecture. So, you have some initial time t1 and a later time t2, and you are given that the say the system is at t1 at initial time q of t1, let us call this q1, q2, and there is some trajectory. So, for every trajectory this is a functional. So, you write this as s of q of t. So, now the action principle tells you that if you take two different you have to extremize this action. So, it is like taking the first derivative of this thing with respect to, so delta s equal to 0 for an extremum. Okay. So, what you are doing is you are playing around with these trajectories. So, the argument of this thing is a trajectory. So, for every trajectory you get a number, and we keep varying the trajectories. So, suppose we have two different trajectories. Okay. So, the key is so these are two different trajectories, and so let us pick some arbitrary time. What you see here is that the trajectories here differ at this thing. So, let us say let us call the two trajectories q prime of t and q of t, And important thing is that we can compare these two things at the same time, like I have done here, and call this object delta q of t. So, we could write it two ways. We could say that q prime of t is equal to q of t plus delta q of t. See, the important point to remember is, if you take two different times, the delta q's at two different times are not correlated, they are independent of each other. So, that statement we will use that to say that delta q at some time t and delta q at some other time tilde is would be 0 when t is not equal to t tilde, but it should be equal to some non-zero quantity, but it has to be the Dirac delta function. We do not say it is 1. If you discretize time, it will become 1, but this is. So, this is just a statement that at two different times the delta q's can be completely independent, they are completely independent of each other. Okay. So, for instance, I could even choose a trajectory which has the following property, that it more or less follows this thing and just has some dip or something in a small region and goes on, and it is more or less the same. So, you can always make that dip as small as you like, and in that sense, so in a limiting sense, you will recover exactly something like this. Okay. So, now the question is, we have to what did we do if we had a function? This is what we would have done, the analogous. So, we would write something like a Taylor series if you have two points. So, let us say f of x prime minus f of x. So, the analogous statement to this would be x prime equal to x plus delta x. So, we would write this as say evaluated when x prime equal to x plus times delta x plus order delta x square. So, we will repeat the same exercise, replacing these functions with functionals. Okay. So, this is just definition. Okay. So, now we look at how we write out the action, which is out here. So, this is what, there is nothing, this is just taking the definition and putting things in here. But now comes the nice stuff, which is to realize that we know that q prime of t is equal to q of t plus delta q of t. Okay. Yeah. So, we can rewrite this if you wish as delta q of t okay. So, what we are doing out here is look what is happening out here, the argument is the same. So, all we are asking is how this function has changed. Okay. So, this is a change in the functional form of this q of t. Okay. So, just for later I will this bar is to just emphasize that this is the change in the functional form. We will see that this is important. Okay. So, one important property, so I will put the bar out here, just reminding you that it is only this thing. And so, then you would like to know what is q dot prime of t. So, but if you are given a trajectory, obviously you can take a derivative, but the important thing to ask is, does delta bar commute with taking derivative? And I would like to recommend that you go home and think about it. Delta bar is such that it will necessarily commute by its definition. Okay. So, q prime would be q dot of t plus delta bar of q dot of t, which I can write now, this particular term can be written as d by dt okay. So, I am allowed to exchange the order of these two things operations, or equivalently it says that delta bar of q determines not just q of t, it determines all derivatives. It is not just for one derivative, even for 100 derivatives we expect it to go through, assuming functions are smooth, etc. Let us not get into those details. Okay. So now you can see that so there are two contributions which come here, one from the first argument changing of this and the second argument. So let us put that in and expand this. This is just a function of two variables. We just need to know, we just need to Taylor expand this to first order. So let us do that. Before I do that, I will not keep writing, the zeroth order pieces will cancel by definition. So it is only the first order piece which will remain. So I will not, otherwise I have got to keep saying this is cancelled, and I will not repeat this. So I will just write out the piece. So there will be two terms, one coming from the first argument changing, okay, times delta bar of q, okay. So far I have not used this part, but I have just written out this thing, and now I will obviously do, I will do the following thing. I will generalize this for more than one degree of freedom. So that would just tell you that, so let us say I runs from 1 to n. So it is just replacing a function of two variables with two n variables. So for each one of them I have to do the same thing, and the only thing which we need is the generalization of this. It is I and j, and I fix that by putting a Kronecker delta. Okay. So what this tells, so first this original Dirac delta function tells you that if you keep take a particular I for two different times, the delta q's are independent of each other. That is what this says. What this says is that if you have two different fields, does not matter even if they are at the same time, their variations are independent of each other. Okay. So that is what is captured by these two things. So now we use the analogous thing out here, and we get so I will not keep writing summation over I, it is obvious that this is a sum over all I. So I can so yeah, let us write it as two steps. Okay. Now I can integrate by parts and make d by dt act on this, so that I can pull out a delta q bar. Okay. So that I could write it exactly like this. So plus there is a surface term which is evaluated at the two endpoints. Okay. So and we choose our boundary conditions such that the surface terms vanish, and now comes this point which I have been emphasizing all through, is the fact that at different times the variations are independent of each other. So out here, so this is an integral over t, that means for every particular time inside this, if this has to vanish, so this should be 0. We already said that we will choose boundary conditions such that the surface term vanishes. So it will only follow if these terms are 0 separately, term by term. Okay. So what you do, so this whole thing can be rewritten to look like this as follows. Yeah. So now you can see that I can rewrite this as delta s So what I am doing here is taking a derivative with respect to delta q tilde, and I will use this formula which we have, which is delta q by the delta qi by delta qj at 2 different times is delta product of the Kronecker delta times delta t minus t tilde. So the first thing you can see is that since I have a delta of t minus t tilde, all occurrences of t become t tilde, and all occurrences of, let us call this j and I become j from the second Kronecker delta. So I just rewrite it as follows. Okay, so the functional, so this object has a right to be called the functional derivative, because it is the derivative of a function with respect to a change in its argument, which is a path. Okay, so this should be 0, of course. That is the Euler-Lagrange equation of motion. Okay, so now the question is, how do we just go ahead and generalize it to the case of a field, and that is not so hard, because all we need to do is to observe that the index j, actually before I do that, maybe for once in this course I will write out for you the next term in how a next term in the analog of a Taylor series for a function would look like for a functional, just for completeness. So for instance, so if you have, so s of some q prime of t will be equal to s at q of t Okay. So roughly speaking, you can just go to a function of many variables, and what you would have got here is a sum over I, next one would have been sum over I and j, so on and so forth, and the same thing is replaced here by integrals. Okay, and you can see that this is a non-local guy, it involves non-local in time, it involves these things, but a functional, this is to be expected. Okay, it is just that the first term is nice and local, okay, and while this is not. Okay. So now let us just ask how, so let me consider the field, and for once I will just separate out the space and time and space part. So you can see that this x variable behaves like the I index in some sense, except it is continuous. So this is, compare it with qi of t. So you can identify this I, which is a discrete index, and you can think of this x as a continuum index, and so now we can ask what would be the analog of this statement. Okay. So delta, first thing is, let us write out what we would define. So what so changing a trajectory would correspond to changing these phi's, okay, and okay. So now, so earlier we only had to worry about these things being local in time, but we also have to choose the, so this is a function has 2 arguments, so you have to compare these things. Even here we did something similar. You would not write, if I put the I index into the story, you would see that you only compare things of the same kind. Okay. So now you can just forget about that detail, and you can see that what we are looking at is a function of many variables t and x, but we are comparing them at the same point in time and space. Better to say that we are comparing them at the same point in time, space time. So now we because we have a continuum, we have a notion of derivative with respect to space as well. Okay. So now you can convince yourself that delta bar of d mu of phi equal to this statement does not need anything beyond these two lines. I mean it is not, it does not refer to anything, because we are comparing guys of the same argument. Okay. So this has to happen, that delta bar and d mu commute with each other, not one derivative, again many derivatives, but for our purposes this is important. Okay. And further we can see that the analog of that statement would be phi of t and x. I will not keeping writing a vector on top of it, it is as many as it is enough for me to mention that there is a spatial dimension. Okay. So earlier what we had was a single delta function in that came from this part, but here again at two different points we expect the field to be independent spatial points, that is. So you will get a Dirac delta function replacing this sort of a thing, a d dimensional Dirac delta function. For every dimension you get a delta function. Okay. So but what we will do is we will just combine all these things and usually write this as a single delta function of just the 4 vectors. We think in terms of d plus 1 dimensional vectors, and if the dimension is specified, one does not even write this thing, it is taken implicitly that it has all the delta functions. Okay. So this is natural generalization. So I and j become continuum, so the Kronecker delta here became this product of delta functions. If you are unhappy with this, what you can do is to go back and look at discretize say time or space, just to understand these examples and see that the if you remember when we did integrals, we saw that summation over I went over to some 1 by a integral dx. You may wonder, shouldn't I have factors of a floating around? You will find that things will go perfectly fine. You will see that there will be a compensatory, if you write a 1 by a here, there would come an a out here, and at least dimensionally you can see the delta function has the correct, I mean so the dimensions etc. will work out perfectly. Okay. So you will get a compensating factor of a's etc. and it cancels away, and so that is the nice way of understanding how a Kronecker delta gets replaced by a Dirac delta function. Okay. So again we need to do the same thing and carry the whole process through, but it is not so hard. Again the rules, the hardest part of the rules are only these things which we already have worked out. Okay. And little bit of notation, this curly delta is different from this partial. Okay. So let's look at this out here. See this this is the functional derivative, while this is a normal derivative. L is a function of its normal partial derivative. Okay. So we distinguish between these two things by this notation. So once you see something, so whenever we write equations of motions in terms of Lagrangians, or now we will see in terms of Lagrangian densities, then we will be writing things in terms of ordinary partial derivatives. Okay. So we need to do the following thing, we have to again work out how okay. So now the first change is that we have a derivative, I mean an integral over both space and time. Again most of the time we just write this as dd plus 1 x. Okay, times. So this is a Lagrangian density. So we need to work out. So there will be this is a function of phi and d mu of phi. So, we have to, so now again it is like a function which has two arguments, I can just take a derivative with respect to that. Okay. But now for every derivative there is so there is not just phi dot, there is also spatial derivatives. So, unlike what we had out here, we get extra terms, but actually if you think about it, it is even that part is there because there is a summation over I. Okay, it is just that so it is there implicitly, but this is what you get. And so now where d mu is the derivative which includes d by dt and this kind of stuff. Okay. So, this is what we get, which is analogous to that, but now we can again use this thing and I can exchange these two terms. Okay. So, now I can again integrate by parts, but now I have to carry out several integration by parts, one for every derivative. Okay. So, we get delta S equal to so I am again I will now from now on I will not separate out t and x, I put them all together. The total derivative piece which I write out here. Okay. So, this is what we get. So, we have to worry about more terms out here. So, the first part so if delta S equal to 0, we will do it in two parts. As always we will say that the object in the curly brackets curly braces is 0, but we will also need this surface term to vanish. So, let us look at the surface term first. So, okay. So, so of course, mu equal to 0, which would give you the time derivative, will look exactly like what we had before. So, let us look at such a piece. So, this is one term which looks like a dt of whatever. This should okay. So, this should be 0. So, this would so you would require that so this implies that the combination that you get dl by dt of phi should be 0. Okay. So, this is exactly like what we had earlier, but now we have some new parts, new terms which were not there earlier, and that comes from the spatial part. So, we have to use the analog of the Gauss divergence theorem for that. So, let us assume that space is just R d, d dimensional space Euclidean thing, and what we do is I will convert these things. I will write this in I'll change I'll think of this as follows. I think of working in the analog of hyperspherical coordinates, because I am not specifying d. If d equal to 3, it will be normal spherical polar coordinates. You choose coordinates which is r and a bunch of angles. Okay. For 3 dimensions it would be theta and phi, the usual coordinates, okay, and dd spatial derivative would, you would write this if you wish in dimensional grounds itself, it will look something like this, r dr minus 1 dr times some angle integration, which I will write as d omega. Okay. So, so now the other part is the spatial part, so which would look like dd of x times some gradient, d dimensional gradient dot this is the term I am just writing out that part. So, now this should be equal to an integral over a sphere of some radius r this is easier than it looks. It just tells you that this is the radial derivative. So, this will pick out. So, if you have a sphere, so what I am doing is I am thinking of getting RD as by taking a sphere, the interior of a sphere, and making the radius of the sphere go to infinity. Okay. I could have done it by putting it in a cubical box, life would be easier, but there is a reason for doing it for later discussion. So, we will want this thing has to be 0, even this term has to vanish. So, now you see that there are conditions you get on this derivative of the spatial derivatives, how they have to appear here. It has to be such that it falls off faster than some. Okay. So, now if you go and look at our particular example, let us look at what that term would be. So, dl by d of grad phi would be up to a sign would be gradient of phi itself. Right. If you look at your Lagrangian density, which was there several boards ago, what you see is that you would get something like this. So, what this tells you is that the radial derivative should fall off. Okay. So, n dot, so we need n dot grad phi to go to 0, faster than plus some epsilon, where some epsilon is some positive thing. If that happens, then I am guaranteed either that, or actually to be we need something weaker than that, delta bar of phi, this thing has to vanish. Okay. So, usually what we will do is we will impose conditions such that these terms go to 0 faster than this. All I need here is epsilon should be some positive number, then it will vanish. Okay. So, so we cannot. So, if you are looking for equations of motion, what it tells you, it is not enough to specify things just at initial and final time things go to I mean the fix the variations, but you need to also worry about spatial boundaries. Okay. I leave you with an exercise which is to consider just R, which is one dimensional space time, one dimensional space or two dimensional space time, where this integral is just a normal integration by parts, and you can convince yourself that this just tells you how things fall off. Okay. So, there this radius, there are no angle, nothing, R is just x, the coordinate. Okay. So, you can see that to make your problem well posed, you better have certain fall off behavior. We will come back to this behavior. This is it is important to remember that there is some fall off. You can't just say I will just solve this whatever set whatever is inside this curly brackets equal to 0 and I am done. That is wrong. Your problem is not well posed. Okay. Yeah, it is d minus 1. In the surface integral, the dr goes away. Thank you. So, this is some hypersphere of radius r, and I just take r to infinity, then I am getting the full boundary. Okay. Thank you. Okay, is this so? Yeah, there is no integral over r because I have integrated by parts in that thing. Okay. But usually what happens is that you will want you know, the energy in your system to be finite, not energy density to be finite. So in such cases you usually find that these conditions are more normally satisfied, okay, in terms of what we will call physical boundary conditions. So that is why quite often we end up not worrying about these issues, we just take the equation. So obviously the object in curly brackets should be set to 0, but I will write that as a functional equation. So delta S of phi this should be equal to 0. So what that will do is, again as before, you get a proper delta function which will take care of the integration, and it gives you this term. So this is the Euler-Lagrange equation of motion. Okay. So we see a slight difference from what we saw in the classical case, in the normal, that there's also spatial derivatives coming out here, but you can see this very nice covariance is actually built in. If your Lagrangian density is a Lorentz scalar, then things are, this object is also by definition a Lorentz scalar, and you have one equation for every point in space, which is like saying that there are as many equations. Okay, so this is just an equation which puts this thing. So this is the Euler-Lagrange equation of motion. Okay. So it's more or less whatever, it's just a repeat of what we did earlier for the case of finite degrees of freedom with some small bells and whistles. Okay. So if you look here, all the Lagrangian densities I am considering, I have not chosen it to be a function to have any explicit time or space dependence. Okay. And this is related to the fact that if you want translation symmetry in space and time. Okay. So has, rather say, the Lagrangian density has no explicit dependence on space time. Okay. And we will show later that this implies that there is a conserved there are okay. So let us see what we mean by this statement. So what you do is this statement is written as follows. So normally what this tells you is that there is some object q which is a constant of motion. In other words, you just take a derivative of it. This is what we mean. Okay, it remains constant through the trajectory of the system once you measure it. Okay. But when we say something is conserved, it's actually we are saying something much stronger than this, and this happens in the context of field theory. What we are saying is that there exists, so this statement is that there exists a 4 current if you are in 4-dimensional space time, or to be more precise, d plus 1 dimensional current j upper mu such that if I separate out the space and the time part in this, you would get something like this. Okay. So this is like the equation of continuity. Okay. So, what this implies is something much stronger than just this global statement. What it says is that, so suppose you have some region sigma in space. So, this is sigma is some bounded some region in space, okay, with some boundary bounded by some surface S. Okay. Mathematical notation for this is to write d of sigma, to write this partial of sigma, but for us. Okay. So, for instance, an example would be to take a say a cubical surface and look at the interior region of that. So, now the boundary of that would be the faces of the cube. Okay. So, you have something like this. So, what this tells you is, suppose you have given me a current like this, I can define Q to be integral I take Q to be the charge which is inside that volume. Okay. Now, the thing is that what would be the charge inside the volume, and if you ask how does it change with time, that would just follow by saying. So, note that even though J0 is a function of t and x, this is only a function of t, because you are integrating out all the x dependence. So, it is just the ordinary derivative of this, but now if you are going to write it inside this thing, it will become the partial derivative. Okay. But now you can see what is happening here, d0 j0 or dt jt is minus of this thing. So, this is equal to, using the equation of continuity kind of, now this is exactly similar to what we had here. Okay. So, now you can again do an integration, except here I chose my thing to be a sort of a ball or with a boundary SR, and then took the limit. Here it is just some finite object, but so this will be this I can rewrite this as some surface integral. I will just write a ds, and there will be some direction, normal direction being at every point at some outward pointing normal, okay, with a minus sign. Okay. So, what this tells you is the rate of change of charge is equal to how much is this is measuring how much is escaping. Okay. So, this tells you that does not matter what is this, how small you take your thing, if you are able to account for all the charge which is going out of the thing and what remains, then so this is in some sense a much stronger statement. Okay. But of course, you could take the integral over, take sigma to be all of space and time, and then, and if there are no currents at spatial infinity, usually you assume there is nothing at infinity, this term just goes away, and then you get dq by dt equal to 0, which is what I wrote first. Okay. So, what I am trying to tell you is that this is a stronger statement than this. I could in principle have total charge conserved, but not locally conserved. Okay. So, this is a much stronger statement, because you can account for what is moving and going, moving from region to region. So, anytime we say that there is something conserved in this course, what we mean is something like this, that something is locally conserved. Okay. So, for instance, so we said that the Lagrangian has no explicit dependence on space and time coordinates. So, let us focus on time. So, So, in classical mechanics, when we had systems where there was no explicit time dependence, we got a conserved we got a constant of motion, which was the energy. Okay. So, just let us so here also, here we will find that we will get conserved quantity, which will be the analog of energy density. So, coming back to this, J0 will be normally identified with this, is we call this charge, it would be charge density. So, if you have energy, you would call it energy density. Okay. So, again we will mimic what one saw in this is what one had in classical mechanics. So, we will just mimic something like this, and I will write, we will prove that all this holds. The analog of J0 here will be okay. So, this will be what we will call energy density. So, I have just used the normal definitions out here. Okay. So, this is what we will get, and so let us work out what this is. So, if you are coming back to our example, we chose L to be half phi dot square minus half gradient phi square minus u of phi. Okay. Of course, this has an argument of x, etc. We are just hiding all those things, because for what we are going to do here, we just will look at where the phi dot appears, and here is phi dot. So, delta L sometimes we will use the symbol pi for this, phi dot will be half, the half goes away, will be just phi dot. Okay. Because there are two things, this is what you get. So, we can put this back here, and we can look at what the Hamiltonian density is. We will prove that this is conserved, etc., but that is not what I want to do. I want to connect up with something in my discussion earlier. So, this would be just phi dot square minus L. Okay. So, now I just plug things in there, I get something very, very nice. Okay. So, these two things came here with a minus sign, and because it appears out here in this fashion, the signs get flipped, and so we end up now getting all positive. So, you can see that these two are positive definite, but u of phi may not be. Okay. So, clearly these are. So, let us ask a condition for which, let us say, the energy, which is the integral over all of space of the Hamiltonian density, should be less than infinity. So, what are the conditions we should have such that it is less than infinity? Okay, the integral over this. Okay. So, it is not enough for these. So, clearly they will impose conditions on each of these terms. So, for instance, suppose you said phi dot were a constant, okay, that looks okay, but if you come here, you put that constant in here, you can see it becomes constant times the volume of space, which is infinite. So, you need certain fall off behavior for things to be finite. So, let us look at there are three terms out here. So, the first term we look at is the phi dot square term. So, again we will see that we can go back and rewrite things in terms of radial direction. So, phi dot square better go as 1 by r power d minus 1 plus some epsilon. Okay. Only then this integral, at least it is a necessary condition. it's not sufficient. If phi dot blows up somewhere in some finite region, that would be a problem at least, but I am just worrying about the conditions at spatial infinity. Phi dot square should go like this, or we should say that magnitude of phi dot should go like 1 by r plus d minus 1 by 2 plus epsilon by 2, but I can just write it as, okay, leave it like this. Epsilon is some positive number, so it should at least fall off like this. It can fall off faster than this. Similarly, gradient of phi square should fall off again similarly, okay, or okay. Otherwise again this term will this. Now going back to this, you look if you look at this, this is stronger than what we required earlier for that thing. Is it stronger or weaker? It is weaker, okay. So this is weaker than that one, we will get to that later, but we are not done yet. What about u of phi? Okay. So now comes the thing, first thing is if you want things to be positive definite, we will require u of phi to be bounded from below. So the third part is conditions on u of phi, bounded from below. By that I mean mod u of phi should be greater than or equal to some constant everywhere for any value of phi, just a function, okay. So it should have a bottom, but let us ask what kind of bottom it can have. Can it have a negative number? Then it will be negative, so you could end up with negative this thing. So you would think that I could settle for a positive number, c can be positive, yes. No, it is bounded from the bottom, okay. I want energy density from below to get, I mean, so I will say greater than or equal to 0, okay. I will, if I put a negative number, then it can become, I want my energy to be positive definite, I can adjust. If it is not so, from what my point here is, suppose it were some constant, I can always add or subtract some constants to make this 0, if it is bounded from below, okay. It need not be bounded from above, there is nothing, okay. So this is just a condition which I will impose. See, the thing is, if it were even a positive constant, it will not violate positiveness, but you will end up getting the minimum value would be that constant times the volume of space. So you always adjust things that way such that it is bounded from below, and it is adjust u of phi to be this way. So you could have so possibilities would be u of phi versus phi, stuff like this. Any, let us draw some functions, it can have many, can go off to infinity, could be something like this, okay. And it is important that there are points which have 0, okay. So now we have come back to the fact that we would like the energy to be not just positive definite, we want it to be finite. So what about this piece? So this implies that u of phi should be, so let us call these specials, that is phi 1, let us call this phi 2, okay, implies that as r tends to infinity, phi should be one of those minima which are 0, which take 0 values, where it takes 0. It can, if it did not, then this will start contributing some finite number. Even something like this, you may think fine, it is a good thing, I can use this point, let us say, let us call this phi tilde 1, but if you put phi tilde 1, this is some finite constant, and that term will blow up. Yeah, no, first step is that, yeah, so I am just saying that whatever happens, it better hit this value at this thing, yeah, it should hit, it should reach one of its 0 values where it becomes 0, it is a necessary condition, okay. So yeah, I mean this is, so this is just to ask the following question, when is this positive definite? and finite. Okay. If you do this, you see that you start getting conditions on the fields. One is not saying that these are all, I mean, like for instance this and this are independent of each other, of course they are, okay. But you can see now, suppose if you had a one dimensional space time, what it tells you is that you can have solutions where the at left infinity it could be phi 1, at the right infinity it could be phi 2, okay. But now we can ask what is the lowest energy which is possible, that would be 0, we will call that the vacuum, okay. And when would that happen? When you look at situations where the fields are space independent and time independent, that means they are constants. But what is the constant value it can take? It can take only phi 1 or phi 2, that would be the lowest energy configuration, it is the 0 energy configuration, and so we call it the vacuum.